Yeah. So today's lecture, I think, is not particularly theoretically interesting. It's pretty straightforward. I don't know if this comes as a relief to you or if you're sort of disappointed. But in any case, we're going to talk about optimization problems. So optimization. So the game of finding where your function is greatest or where your function is smallest. So max, that is to say, max-min problems. Okay. In the setting of functions of several variables. Okay. So right. So you'll have some function, right, and the function will be, say, on the entire space R2. Right? And you'll be wondering, where does that function, does that function reach some sort of maximum value or some sort of minimum value, and where does it happen, and how do you find it? Okay. So to start off with sort of a dumb question, does every function have a maximum value? Or a minimum value? Right. And of course the answer is no, right? Because you're going to have some functions that increase without bound, or some functions that decrease without bound. Now in Calc 1, you should have seen something called the extreme value theorem, okay, which says that if you have a function that is continuous on a closed and bounded interval, if a function that's continuous on a closed and bounded interval, then in fact it's guaranteed to have a maximum value somewhere. So will f has a maximum value in AB, on AB, maybe, on AB, and it also has a minimum value on AB. So there's some place you're guaranteed that it's going to have a max, and you're guaranteed that it's going to have a min, as long as it's a continuous function and it's on an interval that's not it's not infinite, and it's bounded. Okay? I mean, it's closed. Okay. This each of these things is important. Without these conditions, then the statement fails. So, for example, if I look at f of x being 1 over x, say, or no, even simpler, f of x is x on 0, 1. Okay. Right. If I look at it on 0, 1, then you might think, doesn't it have a maximum value? Does it have a maximum value? No. Does it have a minimum value? No. Right? And the reason is that, the maximum, the reason is, if you say it has a maximum value, I would say, well, where does it attain that maximum value? Right? Right? The function is defined on 0, 1, so not 0, 1, not inclusive. Right? If you give me any value, right? If you give me any point x and you say that's where the max occurs, well, I'm going to choose a point slightly to the right between your choice and 1, and say, I just found something that's higher than yours. Similarly, if you're looking for a minimum value, there's no place that you can give me that I cannot choose something farther to the left of it and get a smaller value. Okay, so you see that the closure of this set is actually crucial. Okay. In higher dimensions, so this was for f from AB to R. Now, for higher dimensions, there's an analog. In general, if you have some function on some domain in Rn, and going to R, okay, so you have some function. If f is again continuous on what's called a closed and bounded set, on a closed and bounded set, then you're guaranteed and a min. You're guaranteed that it has a maximum value and a minimum value. Okay. In higher dimensions, what we mean by bounded is that there's some finite ball that contains your set. Okay, so bounded is easy to describe. Your set, there's a finite ball. There's a ball of finite radius containing the set. What we mean by a closed set, however, is a lot harder to describe. And I'm not gonna even try to describe it, but I'm just gonna say that it's the analog of being a closed interval. Like, what does it mean to be a closed set in space? Okay, it actually takes a little bit of doing to describe precisely. There was a couple of years back, some students forwarded me a movie which was of some World War II German movie in German, and it was like Hitler in his bunker talking to his advisors, and he's clearly angry about something. And they've instead of the actual subtitles, some people familiar with mathematics have subtitled it over with Hitler trying to understand the difference between closed and open sets. And he's like, he's like, I have collected the finest topologists in the land to teach me what closed and open means, and yet you cannot describe it to me. And at one point he says, in that case, an open set could be a closed set. And then one guy says, mein Führer, in fact, such sets exist. They're called Klopen. And this everybody out! Everybody! It's hilarious. So like, anybody who thinks this is not bullshit. Of course, everybody's quaking in fear. Okay, so suffice it to say that closed and open is actually a little bit tricky to describe, and we're not going to go into it. Okay. Okay. So let's get back to what we're talking about. You have some set, you have some function. Say it's on R2, and most of what we're going to talk about today is on R2. Okay. So just from some definitions. So if we say, let's say, we say x is a local maximum for f if there exists some ball around x in which some balls say centered on x, it doesn't have to be, but some ball centered on x in which f of x dominates all other values. Let me call this the center x naught. Okay, so f of x naught is going to be bigger than fx for all x in the ball. There's some ball B centered on x in which that is the greatest value. Right. I guess we're in R2, so I should say disk. Some disk. I'm gonna just call it B anyway. Some disk B. Okay, so here is x naught, and there is some disk centered on I'll call it D. There's some disk D centered on x naught, and the value of f of x naught is bigger than all other values. Okay. So locally, you have this, it's a local max, right? It dominates everybody nearby, although it may not dominate everybody in the whole space. Okay. local max. Okay. Local min is described in the same way, right? Just change the sign. Just change the direction here, right? Local minimum, you're going to be smaller than everybody in your neighborhood. We say x is an absolute or global max, or absolute max. If f of x naught is bigger than f of x for all x, period. Right? So if that value is the biggest value you get, then you call that thing the global max. Okay, so it's just an extension of what you do in one variable calculus. Okay. And just like in one variable calculus, you have a first derivative test. Okay. So here it is. If f has a local max or min at some point AB, and the gradient exists there, then what am I going to say? If a local max exists, if you have a local max at some point, right? So there's some point AB, and that thing is, say, a local max. Right? That thing's a local max. Then what can you say about the gradient? Suppose the gradient exists.
Does it equal 0?
It'll equal to 0, right? Because the gradient will be the zero vector. Right? And this should be sort of straightforward, clear to you, right? Because what's the gradient? The gradient is just the vector of partials, right? The vector of partials. The vector of partials. Well, if you take the partial with respect to the first variable, what you're doing is you're slicing a plane through the thing, right? And you're looking at the one-dimensional function, right? And the derivative is going to be 0, right? By your one-dimensional calculus knowledge, you know that the derivative with respect to x is going to be 0. Similarly, when you slice it this way, right? Again, you're going to get one-dimensional function that has a maximum there, and so the derivative is going to be 0. Right? So this is a consequence of your one-dimensional knowledge. So, so proof. Consider g of x being f of xb, h of x being f of ay. I'm sorry, h of y being f of ay. What's the question?
What does it say after some disk?
Some disk D centered on x naught.
Okay.
Some disk D centered on x naught. Right. So these are both one-variable functions that reach maxes at A and this one at B. Right. So just blah, blah, and use the one-variable test. Right. G of x attains a max at A, at x equals A, so G prime of A is 0. Right? But G prime of x is the partial of f with respect to x. Right? So G prime at A is the partial at AB. So that tells you that the partial with respect to x at AB is 0, and similarly the partial of f with respect to y at AB is going to be 0. Okay. So just like in the one variable case, this gives us a way of looking for possible locations of maxes and mins, right? Right. We see that thus, if a max or min, if a local max or min exists at a point AB, we see that either the gradient exists and is 0, or the gradient doesn't exist. Does everybody see that logically, right? If you have a max and the gradient exists, then the gradient is 0. So if you have a max, either the gradient exists and is 0, or the gradient doesn't exist. Okay. Nothing fancy. Okay. Definition. If the gradient of f is a 0 vector, or the gradient of f at AB doesn't exist, we call AB a critical point. Critical point. This just gives some terminology. If the gradient is 0 there, or the gradient doesn't exist, then we say it's a critical point. Really, for us, a critical point is going to be a possible location of a max. Possible location of an extreme value. Okay. Right. That's what's critical about it. Okay. Right. So what we get is that if we're looking for, if you have a local max and min, then it must lie at a critical point, right? So whenever somebody gives you a function, all you need to do is look for critical points, and that will give you all possible places that the maximum or minimum could be. Okay. So here's an example. F of xy, simple, right? F of xy is x plus x squared plus y squared plus 3 minus x plus y over 2 quantity squared. Okay. So maybe take a minute and tell me where the critical points are. Okay. Just as an exercise, differentiation. Okay, it's not all that exciting, so let's just do it together. What's the partial with respect to x? Somebody tell me. 2x minus 3
Yeah. Plus x minus y.
plus x minus y. Thank you. I was afraid you were going to stop there. Don't scare me like that. And then partial this with y. 2y. Anybody?
Plus 3.
Yeah. Plus 3 minus x plus 1. Okay. Right. So what do we get? We get 3x minus y plus 3. We get minus x plus 3y plus 3. Right. Is that right? Wait a second. That's not quite right, right? That's not quite right, in fact. Okay. You get 2x, and then when you differentiate this thing, right, you're differentiating it, right, you pull a 2 down, right? You get 2 times this thing to the 1 times 1/2, right? Right, by the chain rule. Right, so you get 2 times 3 minus x plus y over 2 to the 1 times negative 1/2. Right, the chain rule. Right. Okay. And similarly, for this one, you end up with 2 times y times plus 1/2, 3 minus x plus 1. Okay. Okay. And then if we set the gradient of f to equal to 0, 0, 0, I should say. Set it equal to 0, we get 5x minus y equals 3, and 5y minus x is equal to minus 3, and that gives you that 1/2, negative 1/2 is the sole critical point. In fact, this point does turn out to be an extremum. What do you think it is? Just by looking at this thing here, what do you think it's going to be? Okay, another example. I'll just leave that hanging there to make you uncomfortable. Number 1, f of xy is xy plus 8 over x plus 1 over y. Okay. Yeah, take 2 minutes and see if you can do this one. This one's a little bit trickier. Not as straightforward. See if you can do it. Okay, turn to somebody next to you and say what you're doing. Somebody nearby.
Just trying to solve for x. I got to this part. Yep. And I just got to this partial derivative, and then I'm trying to plug this in for y. And I'm solving it out.
Okay. So so what do you get?
4. Actually,
What do you get? Partial with respect to x is what? Y.
Plus or minus 8 over x squared.
Right, and then partial with respect to y. And then the
X
x
minus
over y squared.
Y squared
Right.
equals 0.
And you set these things equal to 0, right? So you setting each of them equal to 0, we get that y equals 8 over x squared, x equals 1 over y squared. Right. And then,
you plug in 8 over x squared for y.
okay, so so x is 1 over 8 over x squared quantity squared.
And that equals, so x equals x to the 4th over 64.
Okay.
You multiply 64 over, so 64x equals x to the 4th divided by x. And you get the cubic root of 64, which is 4.
Mhm.
And you plug that back in for y, and you get 1/2.
Great. Mhm. Great. Okay, so that gives you, again, a critical point, right? So 4, 1/2 is a critical point. We also have other critical points, right? So along the axes, right? Whenever x is 0 or whenever y is 0, we also have critical points. So also any point x, 0 or 0, y is a critical point.
And you're like, do you plug that into the original or the partial derivatives?
We get that simply by saying that, well, look, the derivative doesn't exist there. Right? Remember, the critical point is where the gradient is 0 or the gradient doesn't exist. Right? Along the axes, the gradient doesn't exist. Okay. Okay. So so then your question becomes, how do you tell what kind of is there a way to tell what kind of extremum you found, right? What type? How can you tell if it is an extremum and what kind of extremum it is? Okay. So here is one thing that we have, and this is in the case of R2. Although I think it can be extended. So given a function on R2, and say that it's twice continuously differentiable. So it has second order derivatives, and those derivatives are all differentiable. We define something called the discriminant of f. It's also called the Hessian. By discriminant of f is going to be the determinant of this matrix. Okay, that is to say you get fxx minus f of x fyy minus fxy fyx. And the second thing, because of the twice continuous differentiability, fxy and fyx are the same thing. So you could write this as fxy squared. Okay. Okay. So here is how we use it. So here's how we use it. We have a second derivative test. It says, suppose you have a function, and it's again twice continuously differentiable. We use we abbreviate this as C2. It's a C2 function, twice continuously differentiable. And suppose that it's a C2 function in an open neighborhood of x naught, of the critical point x naught, y naught. And by neighborhood, I simply mean a disk. I'll use that sort of interchangeably. Okay. So you have some point x naught, y naught, and that turns out to be a critical point, and you know that the function is twice continuously differentiable in some disks around that point. Okay. Then, if the discriminant is bigger than 0, we're going to just abbreviate this as b. If the discriminant is bigger than 0, and the second derivative of the second partial with respect to x is bigger than 0, then in fact x naught, y naught is a local min. If the discriminant is bigger than 0 and fxx is less than 0, then x naught, y naught is a local max. And if the discriminant is negative, then x naught, y naught is neither a max nor min. It's what's called a saddle point. Saddle point is something like so I'm not going to draw you what a saddle point looks like. Okay, let me describe what a saddle point looks like. Saddle point looks like you've got a curve like this, and then you've got these curves hanging off of it. You see what I mean? So if your point is here, then it's not a max because you can always travel up this thing, but it's not a min either because you can always slide down these curves. Okay, so it's a saddle point, neither a max nor a min. Okay. Anyway, this is not particularly exciting. It's just something that you apply. So if you wanted to figure out what kind of extremum, if this is an extremum or not, then you just take the second derivative, take the second partials of this guy, put them in a matrix, and then calculate D, and then use the formula. Okay. Shall we do that in this case? Do people want to do that? Yeah. Okay. Let's do it. Let's figure out what this thing is. Okay. So So our point is 4, comma half. Okay. So we need to calculate, right, these guys, right? So this f sub xx, right? You differentiate this thing again with respect to x, right? And we get what? 16 over x cubed. Is that right? Yes. Right. We differentiate this thing with respect to y, and we get 1. We differentiate this thing with respect to x. We don't have to. It's going to be 1 again. We differentiate this thing with respect to y, and we get 2 over y cubed. Okay. So the discriminant at xy is going to be the determinant of 16 over x cubed, 1, 2 over y cubed. That's to say 32 over x cubed y cubed minus 1. Right? And we just plug in the points here. Right? So the discriminant at 4, comma half, right, is going to be 32 over x cubed. Well, that's 64. And then times y cubed, that's 1/8. So 32 over 8, which is 4, minus 1, so that's 3. Right. And we also see that the second derivative at 4, comma half is 16 over 64, which is 4. Okay, and so that tells you say, okay, well, by the second derivative test, I know that that thing is going to be a local min. Yeah, Laura.
How did you get the 1/4?
This thing?
Yeah.
6. Right, fxx at x is 4, right? So I get 16 over 4 cubed.
Okay.
Right, that's to say 16 over 64. Okay, so simple, right? Simple. You just plug it in and then you use it. It's not particularly exciting. You probably could have guessed that that was going to be a local min just by looking at this thing, right? You can see that as you approach the right, if we're looking at, here is 4.5, say, right? As you approach the x and y axes, the values of your function become infinitely large, right? So the thing is going to go up this way. It's going to have these walls, right, like this, and then it's going to go downwards, right? And then, as you head off this way, it's going to start going up again, right? The xy term, these terms are going to become small, but the xy terms are going to become huge, right? So it's going to do this thing which has like walls and then slopes up that way, right? And so you think, well, what's this thing going to be? It's going to be a min. It's not going to be a max. So you could probably figure it out. Okay. Let me see. Let me do one more example, which will sort of foreshadow the topic of next class. So here it is. So you have a box without a lid, and it's made from 12 meters squared of cardboard. Okay. So, what's the maximum volume? Right. So you're only allowed to use 12 meters squared worth of cardboard, and you have to build the biggest box possible. Okay, but it has no top. You have this box, right? It's got no top on it, right? Let's call this thing x, y, z. Right? Length, width, and height. The volume is, of course, x, y, z, and it's what you're trying to maximize. And we know that 2xz plus 2yz plus 2xy is 12. Right? That's the amount of material that we use has to add up to 12. Right? And we're trying to maximize v, which is x, y, z. Okay. So this is a 3-variable problem, and it also has this constraint on it, which makes it sort of impossible to deal with, or at least tricky to deal with using what we know at this point. Okay. But in this case, you can play a trick, and you say, well, we know that z is 12 minus xy over 2x plus y. Or you could solve for z, say. You could solve for z, and then you can rewrite v, right? V then is going to be 12xy minus x squared y squared over 2x plus y. Right? Because it's xy times z. Right? V was xy times z, and we just rewrote z in terms of x and y. Okay. So then, and now this turns into a two variable thing, right? Because the third variable z depended on the other two, and so we can get rid of it, and right, and then we can just play our two variable game on it, right? So you just check where the gradient equals 0, and you find that in the end you get that x is 2 and y is 2. Okay, which forces z to be equal to 1. Okay. So this is one way of turning a 3-parameter constraint problem into a two parameter no constraint problem. Okay, right? We don't say anything about x and y, right? Whereas here, you notice we're basically, this is a 3-variable. You have some function of 3 variables, and it's to constrain to some sort of surface in the space. Okay, this is an entirely different sort of problem, right? You have a function of 3 variables, and it's constrained to a surface within that space. In fact, a 2-dimensional surface within that space. Okay. So in this one instance, we're able to trick it and make it into a 2-variable problem. Okay. But next time, what we'll see is how to deal with this sort of